5.5 million years ago, the Mediterranean Sea was not there. Where the blue water now stretches between Spain and Africa, between Italy and the long coast of North Africa, there was instead a vast and almost silent desert, 3 to 4 kilometers below the level of every other ocean on Earth, floored in white salt, lit by a hard sun, and almost completely without any water at all. This is the story of how an entire sea vanished, of how, for a span of more than 500,000 years, the basin that holds the present Mediterranean held nothing, or held only scattered pools of brine, a few salt lakes in the deepest hollows, dry rivers cutting their way down toward an ocean that no longer existed. And of the long, slow flood, when it returned, that filled the basin again, in a single great act of geological homecoming, and gave the world the sea it has known ever since. The time is the late Miocene. The age is what geologists today call the Messinian, a small technical word attached to a span of rock that, for over a century, no one quite knew how to read. Around 5.96 of a million years ago, the connection between the Mediterranean and the Atlantic began to fail. By around 5.5 million years ago, that connection was, for long stretches at a time, completely closed. Around 5.33 of a million years ago, the Atlantic broke back through in what geologists today call the Zanclean megaflood, the largest flood that has ever been recorded in the rocks of any age, on any continent in the planet's long history. To understand what happened, the mind has to slow down, has to settle into a kind of patience that has nothing to do with maps or coastlines or the modern blue water of a familiar sea. The events of the Messinian unfolded across hundreds of thousands of years. The empty basin held its dryness for longer than the entire span of human existence, several times over. The flood that ended it, when it came, may have lasted only months, or by some estimates, only a few thousand years. The contrast in timescales is part of the story. Long, slow drying. A brief, vast return. The basin itself is still there. The map of the modern Mediterranean is essentially the map of the dry Messinian basin, simply filled now with water that has been continuously present for the last 5 million years. The deepest parts of the modern sea, the Hellenic Trench south of Greece, the Tyrrhenian basin between Italy and Sardinia, the deep waters east of the Levantine coast, are the same deep places that in the Messinian were the lowest points of the salt-floored desert. The salt is still there, too. Beneath the modern seafloor, in some places more than a kilometer thick, lies the buried record of the long evaporation. Geologists call it the Mediterranean Salt Giant. It is one of the largest single deposits of salt anywhere on the surface of the Earth. This is a quiet story. It is, in some ways, the strangest sleep story that the geological record has to offer. An entire sea, simply gone for 500,000 years. The driest desert on the planet, sitting where the modern islands of the Aegean now lie. The largest flood Earth has ever produced, finally returning the water. And in between, the long stillness of an empty basin, breathing its slow, hot breath beneath an unbroken sky. The night, where the listener is lying, is calm. The Mediterranean, somewhere on the planet, is full of its blue water. It has been full for the last 5 million years. Before that, for 500,000 years or more, it was not. And before that, again, for many millions of years, it was. The basin has been a sea and a desert, and a sea again in the long rhythm of its tectonic geography. Tonight, in this telling, it will be all three. Time for a sea has a different texture than time for a person. A coastline that seems permanent from the perspective of any human life is, on the scale of the planet, a temporary feature, a borrowed configuration of water and rock, held in place by the slow inertia of plates and the steady arithmetic of evaporation and rainfall. The Mediterranean, in any of its ages, has been such a feature. It came into being in something like its present form only 20 or 30 million years ago as the older Tethys Sea closed in around it. It has been a marginal sea for that entire time, dependent on connections to the Atlantic that have widened and narrowed in cycles. It has, in earlier ages, dried partially before the Messinian Crisis brought the great late Miocene drying that this story describes. It will, in some far future, dry again. To settle into such a story is to settle into a different sense of permanence. Things that the eye knows as fixed, the modern coastline, the named cities, the steady blue of a sea on a postcard, become, viewed across deep time, brief settlements of a longer process. The sea is here tonight. It has not always been here. It will not always be here. The basin will hold what the basin can hold in any given age, depending on the slow geometry of its connections to the rest of the world ocean. The story tonight is the story of one particular age of that basin. It is a long age by the standards of any human life. It is a short one by the standards of the earth. To imagine the world the drying found, it helps to imagine, first, the Mediterranean as a much older sea. Long before the Messinian, the basin had been part of a much larger ocean. The Tethys Sea, sometimes called the Tethys Ocean, depending on how its long history is divided, had stretched in earlier ages from the western Atlantic across what is now the Mediterranean and the Middle East, all the way to the western Pacific. It had been an east-west belt of warm water, separating the great northern landmass of Eurasia from the southern landmass that included Africa, India, and Arabia. Many of the most familiar fossil reefs of Europe and the Middle East, the limestones of the Alps, of the Greek islands, of the deserts of Iran, were laid down in the warm, shallow waters of that long Tethyan Ocean. Across tens of millions of years, the Tethys closed. The slow movement of plates brought Africa northward and pressed it into the southern margin of Eurasia. The eastern part of the Tethys disappeared, squeezed between the rising Himalayas and the closing Iranian plateau. The western part contracted into a shrinking series of seas. The Mediterranean, by the late Miocene, was the surviving westernmost remnant of the old Tethys, a smaller body of warm water still connected to the Atlantic on its western edge, but no longer the wide, free ocean it had once been. The shape of that late Miocene sea was already mostly the shape we know now. Italy was a long peninsula jutting south. The Greek peninsula and its islands were broadly in their modern positions, though slightly different in detail, with the Aegean still in the process of forming as a separate sub-basin. Spain and France held their familiar coasts. The North African coast ran approximately where it runs now, from the Atlas Mountains in the west to the Egyptian shore in the east. Sicily, Sardinia, Corsica, the Balearic Islands, Malta, Cyprus, all of these were already in place more or less. What was different before the crisis was the connection. The Mediterranean, in those last million years before the salinity crisis began, was joined to the Atlantic through two corridors. One ran roughly along the path of the modern Strait of Gibraltar, though wider, deeper, less constricted. The other, less familiar to a modern map, ran across what is now southern Spain, the Betic corridor, through the gap between the Sierra Nevada and the Sierra de Aitana, which in those ages was a shallow seaway connecting the Atlantic to the Mediterranean across the Iberian Peninsula. There was also, in some periods, a Rifin corridor in northern Morocco, linking the western Mediterranean to the Atlantic across what is now solid land. The water flowed freely between the two basins. Atlantic water, flowing in from the west, replenished the Mediterranean's losses to evaporation. The salinity stayed close to ocean normal. Marine life, plankton, fish, corals, large pelagic species, moved between the two oceans. The Mediterranean was, in every meaningful sense, a sub-basin of the larger Atlantic with its own particular shape and its own particular ecology, but no fundamental separation from the broader world ocean. Beneath the water, the basin was deep. The Mediterranean has always been a relatively deep sea by the standards of inland water bodies. Its average depth today is more than 1,500 meters. Its deepest points in the Hellenic Trench and the Tyrrhenian Basin exceed 5,000 meters. In the late Miocene, before the crisis, the depths were broadly similar. The basin was a deep, warm marine basin, sustained, like every other ocean basin, by the inflow of water that balanced its evaporation and by the slow, steady tectonics of its surrounding plates. But the tectonics beneath the surface were not steady. They were, in fact, slowly closing the connections. Africa was still pressing northward into Eurasia at a rate of a few centimeters per year. The relative motion was small by any human standard, but unrelenting. Across millions of years, it had been narrowing the corridors that fed the Mediterranean. The Betic corridor in the late Miocene was already shoaling, its bottom rising as the Iberian Peninsula and the African plate compressed against each other. The Gibraltar connection was narrowing. The Rifin corridor was uplifting and closing. The future of the basin's connection to the Atlantic was slowly being decided by the geometry of plates whose movements no creature alive at the time could have observed. The closure, when it came, did not happen all at once. The corridors shoaled gradually across millions of years. By around 6.5 million years ago, the Betic corridor had become shallow enough that the deep, dense Atlantic water could no longer flow through it freely. The exchange between the two oceans began to be restricted. Even before the full closure, the chemistry of the Mediterranean started to shift. The deep waters became saltier as evaporation continued at its normal rate, but inflow could no longer fully replace what was lost. The fossils of certain deep-water organisms, particular foraminifera, particular ostracods, began to disappear from the sediment record, replaced by species that could tolerate higher salinity. The slow, quiet warning of a basin beginning to choke was already in the rocks. By around 6 million years ago, the Betic corridor had effectively closed. Only the Gibraltar connection remained. The Rifin corridor in northern Morocco was likewise closing or had already closed. The entire freshwater inflow of the Mediterranean, from the rivers, from rain, from the direct exchange with the Atlantic, now depended on a single narrowing strait, less than 15 kilometers wide at its narrowest, growing shallower year by year as African and European tectonics continued to press the gap toward closure. The mathematics of evaporation in such a basin is unforgiving. The Mediterranean, then as now, lay in a warm, dry latitude. Its evaporation rate across its entire surface area is roughly 5,000 cubic kilometers per year. Its rivers, the Nile, the Po, the Rhone, the Ebro, the Adige, the long string of smaller rivers from Spain, Greece, and the Levant, bring in only a fraction of this. The remainder, in normal conditions, has to come from the Atlantic. Through the Gibraltar connection in the modern day, a vast volume of Atlantic water flows in along the surface, while a saltier Mediterranean current flows out below. The two-layer exchange keeps the basin's chemistry balanced. In the late Miocene, as Gibraltar narrowed and shoaled, this exchange began to break down. The two-layer flow could no longer sustain itself. The deep outflow of saltier water was choked first. The sill at the bottom of the strait was rising, and dense bottom water could not pass over it as easily. Then, the surface inflow itself was reduced, as the constriction of the strait limited how much Atlantic water could enter. The basin's losses to evaporation began to exceed its gains. The water level slowly began to drop. The first signs of the drop are recorded in the rocks of the Mediterranean coast, in Sicily, in southern Spain, in the Greek islands, in Crete, in Cyprus. The late Miocene rocks show, in their layers, the slow rise of unusual minerals. Gypsum, calcium sulfate, began to precipitate out of the increasingly saline water and was deposited on the floor of shallow areas as the water above became saturated with respect to it. Gypsum, in nature, only forms when the salinity of seawater rises to about 3 or 4 times its normal value. To find it across multiple basins simultaneously is to find evidence that the entire Mediterranean had become hypersaline. The first stage of the salinity crisis had begun. This stage, called the lower evaporite phase by geologists today, lasted for several 100,000 years. The Mediterranean, during this time, was not yet empty. It was still a sea of sorts, a hypersaline sea with a much higher salt content than ordinary ocean water, periodically refreshed by partial inflows from the Atlantic, when storms or sea level cycles briefly opened the Gibraltar connection wider. Each pulse of hypersaline conditions left another layer of evaporite minerals in the basin. Each partial refreshment dissolved some of those layers and laid down new sediment from the temporarily revived sea. The rocks today, in places like Sicily and Cyprus, preserve a striking interbedded pattern, alternations of evaporites and more normal marine sediment, recording the long, halting struggle of the basin to maintain its connection to the broader ocean. The struggle, in the end, was lost. The pattern of opening and closing in those last hundreds of thousands of years before the full crisis has been read in remarkable detail from the rocks. The shallow shelf seas of southern Spain, of Cyprus, of Sicily, all preserve in their Messinian sediments alternating layers. First, a layer of fine, organic, rich mud, recording a brief reconnection to the Atlantic and a return to more normal salinity. Then, a layer of gypsum, recording the renewed drying. The cycles, when measured carefully, match the rhythms of Earth's orbital variations, the slow wobble of the planet's axis, the periodic stretching of its orbit, the gentle tilt and untilt of the spin. These orbital rhythms drive small changes in global climate on scales of tens of thousands of years. In a basin balanced on the edge between dryness and inflow, those small changes were enough to push the basin back and forth across the threshold of full closure. Each wet phase, each dry phase, each gypsum layer, each return to mud. Layer by layer, the rocks read the slow breathing rhythm of a sea that was, for a long time, almost dying, and that in the end did die. Reading these rhythms is one of the great quiet achievements of late 20th and early 21st century geology. It has required the patient measurement of thousands of layers, the dating of each by stable isotopes and by orbital tuning, the careful matching of records from one basin to another. The result is a chronology of the late Messinian that is precise in many places to within a few thousand years across a span of 500,000. The Mediterranean's last breaths before the great drying can be counted, layer by layer, almost as if the basin were keeping its own diary. Around 5.5 million years ago, the Gibraltar connection closed completely. It is not certain whether the closure was tectonic, a final uplift of the strait that raised it above sea level, or whether it was sedimentary, with the strait silting up. Both processes were probably involved. Either way, by some moment in the late Miocene, no Atlantic water was reaching the Mediterranean. The basin was, for the first time in many millions of years, completely cut off from the world ocean. Without that inflow, the mathematics took over. 5,000 cubic kilometers per year of evaporation, partially offset by the rivers and the rain, but not nearly enough. The Mediterranean's net water loss after the full closure has been estimated at around 3,000 cubic kilometers per year. The basin holds today about 3.5 million cubic kilometers of water. At a net loss of 3,000 cubic kilometers per year, an undisturbed basin would empty in roughly 1,000 years. 1,000 years. Long enough that no individual creature could have witnessed the entire change, short enough, in geological terms, that it was effectively instantaneous. Within a span shorter than the age of the oldest human civilizations, the entire Mediterranean Sea drained dry by evaporation. The water vapor rose into the atmosphere, drifted on the trade winds, fell as rain elsewhere, into the Atlantic, onto the African continent, onto the Eurasian landmass to the east. The molecules of the old Mediterranean dispersed into the world's water cycle, became other rains, other rivers, other oceans. The basin, where they had been, was empty. What was left in their place was salt. A sea, when it evaporates, leaves behind everything it had dissolved in itself. Sodium chloride, the table salt of the kitchen, calcium sulfate, the gypsum of plaster and wallboard, magnesium chloride, calcium chloride, potassium chloride, and many smaller traces of other minerals. As the Mediterranean evaporated, these minerals precipitated out in stages as the remaining water became more and more concentrated. First, the carbonates, in the very earliest stage, when the water had only slightly thickened. Then the gypsum, as the salinity rose to about 4 times normal. Then the halite, the rock salt, as the salinity reached about 10 times normal near the absolute end of the evaporation. And finally, in the deepest, hottest, most concentrated remaining brine, the bittern salts, the magnesium and potassium chlorides, which only crystallize when the original sea has been concentrated to nearly its last fraction. The result, on the floor of the empty basin, was an enormous sheet of evaporite minerals. In some places, the salt giants accumulated to over 1 kilometer in thickness. In others, less, but still hundreds of meters. The total volume of salt left in the Mediterranean basin during the Messinian Salinity Crisis has been estimated at around 1 million cubic kilometers, about 5% of the total dissolved salt content of the modern world ocean. To deposit that much salt on the floor of a single basin in a few 100,000 years requires the complete drying of a sea the size of the modern Mediterranean several times over. It is one of the largest evaporite deposits in the entire geological record. The evidence for this is unambiguous. Beginning in the 1970s with the famous Glomar Challenger expedition of the Deep Sea Drilling Project, recovered cores from beneath the modern Mediterranean seafloor that contained at depth thick layers of the characteristic evaporite minerals. The cores told a clear story. The modern Mediterranean is sitting on top of a buried desert. The salt is there. It has been there since the Messinian. It is too thick to have formed in any other way than the complete drying of an entire enclosed sea. The empty basin, when it had drained, was a strange place. It was deep. The deepest parts of the modern Mediterranean seafloor lie 3 to 4 kilometers below the surface of the modern sea, which itself is at the same level as the Atlantic. With the basin drained, those deepest points were now 3 to 4 kilometers below the level of every other sea on Earth. The atmospheric pressure at the bottom of such a basin, roughly 30% higher than at the modern Mediterranean surface, would have been one of the highest atmospheric pressures anywhere on the planet's surface, comparable to what is found in the deepest parts of the modern Dead Sea region, but on a continent-spanning scale. The boiling point of water at such pressures is several degrees higher than its sea level, meaning that, even with summer temperatures of 50 degrees or more, water could remain liquid in the deepest brine pools that survived in the basin's deepest hollows. The temperature on the floor of the empty basin would have been extraordinary. Air sinking 3 to 4 kilometers from the surrounding rim into the basin compresses adiabatically, heating up by about 10 degrees Celsius per kilometer of descent. The summer surface temperatures around the Mediterranean rim in the late Miocene were already high, perhaps 30 to 35 degrees Celsius in the warmer regions. By the time that air had sunk to the floor of the basin, it would have been compressed and heated to perhaps 70 or even 80 degrees Celsius, hotter than any continental surface today. Even in winter, the basin floor would have been warmer than its surroundings by tens of degrees. It would have been one of the hottest places on Earth. The light in the basin would have been hard. The dust and haze from the salt flats would have given the sun a coppery, washed-out quality. The salt itself, where it lay in clean, fresh sheets, would have been blindingly white in direct sun, glittering in the heat shimmer. Old shorelines, terraced into the rocks of the basin's edges, would have stood as evidence of the previous higher water levels. The rivers, the Nile, the Rhone, the Po, flowing toward the basin from the surrounding land, would have cut deep canyons down through the older sediments, descending toward whatever standing water remained at the lowest points. These canyons are still preserved beneath the modern seafloor and along the modern coasts. The canyon of the ancient Nile, the so-called Aeon Nile, was cut more than 1,000 meters deep into the bedrock during the Messinian and is now buried beneath the more recent sediments of the Nile Delta. Similar canyons run beneath the deltas of the Rhone, the Po, and most other major Mediterranean rivers. They are the long, dry signatures of rivers that were once forced to flow down to a sea level 4 kilometers below the modern shore. In the lowest parts of the basin, scattered hypersaline lakes would have persisted. Their waters, even hotter and saltier than the Dead Sea today, would have been near or beyond the limits of any familiar life. Microbial mats, the simplest forms of life still capable of surviving in such conditions, may have lined their shores, slowly building stromatolite-like structures of salt and biofilm. Other lakes, fed seasonally by river inflow from the surrounding continents, would have been fresher, supporting fish and other aquatic life that survived as relict populations in their isolated waters. The Mediterranean basin, during the long dry, was not entirely lifeless, but it was a place of extreme salinity, extreme heat, extreme isolation, and extreme strangeness. Walking, if a person had walked there, would have been almost impossible in the depths. The salt flats in many places would have been crusted, brittle, hot to the touch. The air would have been hard to breathe, heavy with humidity, hot beyond the comfort of any modern desert. The horizons would have been distant, the light glaring. The silence would have been absolute, except for the wind across the salt and the occasional distant rumble of falling rock from the basin's eroding rim. It was, in every meaningful sense, the most extreme landscape this side of the polar ice, and it lay, for hundreds of thousands of years, where the modern Mediterranean now lies. The geography of the empty basin had its own internal structure. Sicily, which today is an island, would have been part of an enormous land bridge connecting Italy to North Africa. The shallow Strait of Sicily, between the modern island and Tunisia, was at that time a high ridge separating the western Mediterranean basin from the eastern. With the sea level dropped by several kilometers, the ridge stood as a continuous chain of high ground from the Apennines, down through Sicily, across to the Atlas Mountains. Animals could have walked across that bridge, though the deep, hot lowlands on either side would have been almost impassable barriers. Other islands of the modern Mediterranean, Sardinia, Corsica, the Balearic Chain, Cyprus, Crete, would have been highlands rising from the dry basin floor, surrounded by salt flats rather than by water. The view from such a highland would have been remarkable. From the cliffs that are today the southern shore of Crete, looking south, an observer in the Messinian would have seen no sea. They would have seen, instead, a vast lowland falling away in stepped terraces toward a glittering distant haze. The salt flats, kilometers below, would have shimmered in the heat. Beyond them, on the southern horizon, the highlands of North Africa would have risen, but those highlands would have been farther away than they are today, since the lowlands between them would have been much wider with the basin drained. The whole geography, from the modern Aegean to the modern Levant, from southern Italy to North Africa, would have been transformed. It would have been a continent of dryness, with isolated highland archipelagos rising from a salt-floored desert that ran from Gibraltar to the Levantine shore. The salt giants beneath the modern sea floor are the long memory of that drying. In some places, the salt is over a kilometer thick. In others, it is hundreds of meters. The total volume across the entire Mediterranean basin is enormous. To deposit that much salt requires the complete evaporation of a sea volume of water many times over, between 30 and 40 times, by some estimates, accounting for the fact that each cycle of evaporation only deposits a fraction of the total dissolved salts. This means that, during the Messinian, the basin must have been refilled and re-emptied many times. The Atlantic connection was not simply closed once, all at once, and reopened in the Zanclean flood. It was, instead, intermittently leaky. It opened and closed in pulses across the long duration of the crisis. Each opening allowed a partial refill from the Atlantic. Each closing was followed by another evaporation. Each evaporation deposited another set of evaporite layers. Over hundreds of thousands of years, layer upon layer of salt accumulated until the basin floor had been buried beneath the salt giant we know today. The detailed structure of the salt giant is more complex than a simple stack. The bottom layers, oldest, are made of gypsum, the calcium sulfate that precipitates first as a sea concentrates. Above the gypsum is the main halite layer, pure rock salt, deposited in deep persistent dryness. Above the halite are more complex evaporites, including the bitter minerals that crystallize only when the brine has been concentrated to its last few percent. Above those, in some places, are upper gypsum layers, recording one or more later returns to less extreme salinity, where calcium sulfate could precipitate again before the basin re-emptied. The final cycle, at the top of the evaporite sequence, gave way to the deep marine sediments of the Zanclean, the layer that records the catastrophic refilling and the establishment of the modern Mediterranean Sea. In some places, the salt giants have moved. Salt, under heavy pressure from the overlying sediments, behaves like a slow plastic. It flows, it rises. Over millions of years, in places where overlying sediments have built up unevenly, the salt is pushed upward in domes, salt diapirs that pierce the overlying rocks and reach close to the modern sea floor. These diapirs are visible in seismic surveys of the modern Mediterranean. They are part of why the basin's geology is so complex. The salt is not a passive layer at depth. It is an active, slowly moving body of evaporite that has been redistributing itself for the last 5 million years, ever since it was deposited. The salt has economic value. Some of it has been mined where it reaches the surface. Sicily, in particular, has long been a center of evaporite mining. The gypsum and halite deposits exposed in the hills of the central island are part of the upper Messinian sequence and have been quarried since antiquity. The white quarries above Mount Etna, the salt of the Sicilian interior, the gypsum panels and statues that decorated Greek and Roman buildings, all of these were drawn from the buried memory of the Messenian. The dryness of an ancient sea has been quietly serving the construction of human civilizations for thousands of years. The salt is not, in the broad geological sense, exceptional. The earth has produced many salt giants in many ages in many basins. The Permian salts of Central Europe, the Jurassic salts of the Gulf of Mexico, the Cretaceous salts of Brazil and West Africa. All of these record the drying of long-ago seas in similar ways. The Messinian is not unique in its character. What makes it remarkable is its recency. It happened only 5 million years ago, yesterday in geological terms. The basin where it happened is not buried under a continent. It is the modern Mediterranean. The shoreline that stood at the rim when the basin was dry is the same shoreline that holds the cities of Rome, Athens, Alexandria, Tunis. The dryness is recent enough that it feels, in a way that older salt giants do not, almost touchable. In the long dryness, life persisted in scattered places. The deepest hypersaline lakes in the lowest hollows of the basin were too salty for almost anything. But certain microbial communities adapted to extreme salinity, related to the modern microbes of the Dead Sea, of Utah's Great Salt Lake, of the salt pans of the world's other extreme environments, lived in those waters. They formed thin biofilms on the salt surfaces. They built layered structures similar to the ancient stromatolites of the early Earth, where their slow growth interacted with the precipitating salts. They lived, ate, reproduced, and died in conditions that would have killed almost any larger organism within minutes. They were the deepest survivors of the long crisis, holding the basic chemistry of life in places where no other life could go. In the slightly fresher pool, where rivers from the surrounding continents flowed in, and where evaporation had not yet reduced the water to brine, small relict populations of fish and other aquatic life held on. The fossil record from certain Messinian deposits in southeastern Spain, in southern Sicily, in Tunisia, includes fish that had retreated from the disappearing main basin into these refugia. Some of them are species that had been widespread in the late Miocene Mediterranean. Some are new forms, isolated in their pools long enough to have begun evolving into distinct species. The genetic isolation of the dry Mediterranean, like the genetic isolation of any island chain, was a small engine of evolution. New forms emerged. Some of them, when the flood eventually returned, would survive into the modern Mediterranean in modified form. Around the edges of the basin, on the high rim, life continued more or less as it had before. The forests of southern Europe and northern Africa in the late Miocene were similar to the forests we know, with mixtures of conifers, oaks, and other broadleaf trees in patterns shaped by the Mediterranean climate. Mammals walked these forests, Early antelopes, primitive horses, a great variety of pigs and deer, the ancestors of modern carnivores. Hominid ancestors, the great apes from which our own line descends, lived in some of these forests in southern Europe and East Africa. Their lives on the rim would have included occasional descents into the upper canyons of the dry basin, perhaps to follow rivers down into cooler valleys or to scavenge from the unique ecosystems of the salt pan margins. Some fossil evidence suggests that early hominins did indeed range across landscapes that would, in the Messinian, have been dramatically dry. It is a strange thought on a quiet evening to consider that the immediate ancestors of the human family walked the rim of an empty Mediterranean basin. They did not know what they were looking at. They did not know that in another 5 million years the basin would hold the sea around which their descendants would build civilizations. They only saw, in their immediate moment, a vast, hot, salt-crusted lowland with the rivers of their continents pouring down into it, and the rare, distant glimmer of one or another hypersaline lake catching the sun on the floor below. Some of them perhaps drank from the rivers near the rim. Some perhaps descended into the upper canyons. The marks of their lives are scattered, faint, fossilized. The basin they looked into is now a sea. The line that they began continues tonight in the body of the listener and in every person alive on earth. There's a particular kind of stillness in considering the scale of these inheritances. The ape-like ancestors of the human line in the late Miocene were small, forest-dwelling primates. They lived mostly in trees. They ate fruit, leaves, occasional small animals. They had not yet evolved the upright walking that would, in another 2 or 3 million years, begin to define their descendants. They did not yet have hands of the modern shape or brains of the modern size. They were, in almost every visible way, animals like any other, quiet, mortal, locked into the small concerns of their own immediate lives, and yet, in their bodies, they carried the genetic foundation of every human alive today. Every gene that codes for a modern protein, every regulatory sequence that controls modern development, every basic structure of the modern primate body, the spine, the rib cage, the 4-chambered heart, the patterned brain, was already present in those ancestors. They were, in every meaningful sense, our forerunners. They lived through the Messinian. They saw, in the small portion of their range that overlapped the Mediterranean rim, the great drying. And they continued. Their descendants survived the Zanclean refilling. Their descendants survived the Pliocene cooling, the Pleistocene ice ages, the slow drying of the African savannas, the long march out of Africa, the spread across every continent. The line, unbroken, runs from those small late Miocene primates to the body that is breathing now on this calm evening, listening to the long story of a sea that had once been a desert. The flood, when it came suddenly. For 500,000 years, the Mediterranean basin had been mostly empty. The Atlantic had been blocked. The salt giants had grown layer by layer on the basin floor. The hypersaline lakes had come and gone in the deepest hollows. The rivers had cut their long canyons down toward the dry base level. The basin had settled in a quiet, hot, empty kind of way into its prolonged Messinian state. And then, around 5 33/100ths of a million years ago, the Atlantic broke through. The breach happened at Gibraltar. The exact mechanism is still debated, whether it was a tectonic uplift on the Atlantic side that finally raised that ocean's water above the level of the strait's sill, or a marine erosion that gradually cut a channel through the closed barrier, or some combination of the two. What is clear, from the geology is that once the breach began, it accelerated. The Atlantic water flowing over the barrier into the deep dry basin 3 to 4 kilometers below sea level eroded the channel as it flowed. The channel deepened. The flow increased. The deepening and the increasing flow reinforced each other in a runaway process over weeks to months. At the peak of the flood, the rate of inflow may have been 1,000 times the modern flow rate of the Amazon River. By some estimates, perhaps 100 million cubic meters per second of Atlantic water were pouring over the Gibraltar threshold and falling through a combination of cataract and high-velocity sheet flow into the empty basin. The basin began to fill at rates of meters per day in some scenarios, possibly tens of meters per day at the peak. The total volume of water moved was on the order of millions of cubic kilometers. The energy released as that water fell from sea level to the basin floor 4 kilometers below was equivalent to a substantial fraction of the total energy budget of the entire Earth's climate system, concentrated in a single, brief, catastrophic event. This was, by every available measure, the largest flood in Earth's history. There's been no comparable event since. The glacial outburst floods of the Pleistocene, which carved out the channeled scablands of eastern Washington state, were vast, but smaller in total volume by orders of magnitude. The mythological floods of various human cultures, even taken at the most literal interpretation, are tiny by comparison. The Zanclean flood, when it filled the Mediterranean, was a planetary event on a scale that no human or animal observer has ever witnessed in any subsequent age. The marks of that flood are still in the rock. Below the Strait of Gibraltar on the floor of the modern sea, geophysical surveys have mapped a vast erosion channel, a buried canyon 200 kilometers long, cut into the bedrock during the violent inflow. The channel is filled today with the Pliocene sediments of the modern Mediterranean. Its shape, hidden beneath the recent sea floor, was only fully revealed by seismic imaging in the early 21st century. It is the largest known erosion feature of its kind anywhere on Earth, a single immense channel cut by a single brief flood in a few months to a few years that brought the Mediterranean back from the dead. How long the entire refilling took is debated. Some models suggest a few months for the deeper basins to fill. Others suggest a few thousand years. The geology is consistent with rapid, perhaps catastrophic, filling. The sediments of the Zanclean record a quick transition from the dry Messinian conditions to the deep marine conditions of the new Mediterranean, with no long intermediate phase. By any account, in less than a few human lifetimes, perhaps in less than a single one, the basin that had been empty for 500,000 years was, again, a sea. What it would have been to stand on the rim during the flood is almost beyond imagination. The sound alone would have been overwhelming. The roar of a cataract many times wider and taller than Niagara, sustained for months. The mist from the falling water would have risen kilometers into the air, visible from far inland on either continent. The temperature near the falls would have been cooler than the surrounding desert as the rising mist absorbed heat. The ground near the eastern lip of the breach would have been shaking constantly with the impact of the falling water on the rock and salt below. In the deep basins, the water would have arrived first as a distant sound, then as a rising humidity in the air, then as a slow, lapping front advancing across the salt flats at perhaps a few kilometers per day in the early phases, faster as the cataract widened. Within months, in some scenarios, the water level in the deep eastern basin might have risen by hundreds of meters. Within a year or two, the entire basin floor, millions of square kilometers of salt-crusted desert, would have been under deepening water. The hypersaline lakes of the dry phase would have been overrun. The microbial mats would have been buried. The dry canyons of the Nile, the Rhone, the Po would have been, for the first time in 500,000 years, drowned in seawater from below. For any creature alive on the basin floor, and there were some in scattered refuges, the flood would have been the end of their world. For creatures on the rim, the change would have been visible only as a slow rise of the water in the basin below, a quiet, decades-long return of the sea, completing itself before any individual large mammal could have lived through the entire process. The flood was geologically brief. By any biological measure, it was a long event. By any planetary measure, it was instantaneous. The water, when it had filled the basin, settled into the modern Mediterranean. Atlantic water, once the breach had widened and stabilized at Gibraltar, continued to flow into the basin in much the way it does today, a surface inflow of less salty water from the Atlantic, balanced by a deep outflow of saltier Mediterranean water back into the Atlantic. The two-layer exchange, the same exchange that maintains the modern Mediterranean's chemistry, established itself again. The basin filled to a level that approximately matched the Atlantic. The sea, in its full modern form, was back. The chemistry of the new sea in its earliest centuries would have been somewhat unusual. The remaining hypersaline brines of the empty basin, mixed into the Atlantic inflow, would have produced a Mediterranean that was, briefly, saltier than normal. The sediments of the earliest Zanclean record this brief hypersalinity. Then, a gradual dilution toward modern Atlantic similar conditions. Within a few thousand years, perhaps a few tens of thousands at most, the Mediterranean's chemistry had settled into the pattern it has held ever since. The biology of the new sea was also new. The previous Mediterranean fauna, the ones that had lived in the late Miocene before the crisis, were largely gone. The hypersaline lakes had killed most of them. The empty basin had eliminated their habitat for 500,000 years. When the Atlantic returned, the new sea had to be repopulated almost entirely from Atlantic stock. The fish, the corals, the pelagic species, the benthic invertebrates, almost all of them are descendants of Atlantic populations that swam in through the new Strait of Gibraltar in the Zanclean and the early Pliocene. A few relict populations from the dry period refugia survived in some basins, but the broad biological character of the modern Mediterranean is Atlantic, with regional differentiation acquired over the last 5 million years. The basin geometry, after the flood, was largely the same as before, but the salt giants on the floor were now buried beneath an increasingly thick layer of marine sediment. The slow, ongoing accumulation of Pliocene and later sediments has, by now, buried the Messinian evaporites under hundreds to thousands of meters of younger rock. Only in places where the salt is flowed upward as dye appears, or where the underlying salt is closer to the surface, do the deposits come within reach of modern drilling. In the open basins, the salt giants are deep enough that they are essentially invisible from the surface, except as features in seismic surveys. Today, the Mediterranean continues to function as a sub-basin of the Atlantic. Evaporation still exceeds inflow from rivers and rain by a substantial margin. The deficit is made up, as it always has been, by Atlantic water flowing in through Gibraltar. The two-layer exchange, the slow turnover, the careful chemistry, all of these continue in the same way they did before the crisis, before the salt giants began to form. The basin has been a normal marine sea for the last 5 million years. The dryness is in the past, but the basin is still moving. Africa is still pressing northward into Eurasia at the same few centimeters per year that it has been moving for tens of millions of years. The Strait of Gibraltar is not stable. In the long future of the planet, in another 5 or 10 million years perhaps, Africa may close the gap again. The Mediterranean, in that distant age, may dry once more. The cycle that played out in the Messinian is not unique in the basin's history and may not be the last. The Earth, on its long time scales, repeats itself. The sea that the listener knows today is, in the very long term, a temporary sea. The rocks of the Messinian still hold their long story. In southern Spain, in the gypsum cliffs of the Sorbus Basin, the lower evaporite layers of the Crisis are exposed in great vertical sections. A geologist walking through those cliffs can read the slow change in salinity through the layers, layer by layer. Below, the more normal marine sediments of the late Miocene. Above them, the first thin gypsum bands, then thicker gypsum. Then, in the upper sections, transitions toward the more arid evaporite stages. Each layer is dated by its position relative to other layers and by the orbital cycles encoded in the bedding rhythms. The chronology is now precise to within a few thousand years across the entire Crisis. In Sicily, the upper Messinian deposits are exposed across much of the central island. The famous gypsum quarries near Caltanissetta, the salt mines near Realmonte, the white cliffs of the southern coast, all of these expose the salt giant in places where it has been brought to the surface by tectonic uplift. The Sicilian succession is one of the best studied evaporite sequences in the world. It has been used for over a century to define the stages of the Crisis, to test the chemistry of evaporation, to refine the chronology against orbital cycles. In Cyprus, the Messinian is exposed in the southern part of the island, in cliffs that show the same broad pattern. Drilling and seismic surveys have mapped the buried evaporites beneath the modern coast and continental shelf. In North Africa, the Saharan margins of the Mediterranean show the deep canyons of rivers that drained to the basin during the dry phase, now partly filled with younger sediments. In the Balearic Islands, in Sardinia, in southern France, the Messinian has been mapped in detail in many sections. The chronology of the events, refined by decades of careful work, is now widely agreed. The Crisis began around 5 96/100ths of a million years ago. The full closure of the Atlantic connection was around 5.5 million years ago. The deepest dry phase ran for several 100,000 years. The Zanclean flood, which ended the Crisis, occurred around 5 33/100ths of a million years ago. The total duration of the dry period basin, in its various forms, was about 600,000 years. The mechanisms, tectonic, climatic, hydrological, have been worked out across many lines of evidence. The salt giants have been mapped, the buried canyons have been imaged, the Zanclean flood channel has been measured, the orbital tuning has been calibrated, the fossil records have been classified. The biological recovery has been traced through the early Pliocene sediments. The story, taken as a whole, is one of the more fully understood events in the entire geological record. There remain debates in the details. There always do. But the broad shape is clear and has been for decades. What is striking is how recent it all is. 5 million years is not long. The hominin lineage, which would eventually produce humans, was already alive when the Mediterranean dried. The continents, the mountain ranges, the major rivers were already largely in their modern positions. The world of the Messinian is recognizable as the same world we live in today, only with one of its inland seas absent and a great desert in its place. The night is quiet. The Mediterranean, somewhere on the planet, is holding its blue water in the basin where, 5 million years ago, there was no water at all. The salt giants are still there, beneath the sea floor, kilometre-thick reminders of the long dryness. The Zanclean flood channel beneath the Strait of Gibraltar is still buried, the great erosion scar of the day the Atlantic returned. There is no message in this. There is no warning. The Messinian was not a lesson. It was a length of geological time in which one particular basin on one particular planet lost its water and then regained it. It happened. It ended. It left behind a sea, a salt giant, a buried canyon, a slightly altered biology, and a quiet record in the rocks for geologists much later to read. The basin will dry again in the deep future. The basin has dried before in older closures. The pattern is part of what the Mediterranean is, a sea that by accident of geography sits between two slowly converging continents in a latitude where evaporation always exceeds inflow, dependent on a single narrow strait for its connection to the broader world ocean. Its existence, in any age, is a borrowed condition. It has been borrowing the water from the Atlantic for the last 5 million years. Before that, it had not been borrowing it for 500,000 years. Before that, again, it had been borrowing it for many millions. The arithmetic of the basin is patient and reversible. The atoms of the Messinian water, when it evaporated, went elsewhere. They became other rains, other rivers, other clouds, other oceans. The same atoms have been moving around the planet for the entire age of the Earth. They have been Mediterranean before, they have been Atlantic before, they have been deep ocean, surface lake, polar ice, atmospheric vapor, river. They will be all of these things again. The water of the present Mediterranean, which the listener has perhaps swum in or stood beside or merely seen on a map, is in continuous slow exchange with all of the other waters of the earth on timescales that range from days to millions of years. There is no need to hold on to any of this. No image needs to be remembered. The dry basin, the salt floor, the long flood, the modern sea, all of them will stay in the rocks, in the deep records of the earth, with or without anyone hearing the story tonight. The Messinian will remain a small, well-studied chapter in the long history of the planet. It will keep being there, in the textbooks, in the field guides, in the seismic profiles below the modern sea, for as long as there are humans interested in such things, and for much longer than that, in the silent record of the rock itself. Let the dry basin continue, somewhere in the buried memory of the salt giant. Let the Zanclean flood keep falling, somewhere in the slow geology of the earth. Let the modern sea hold its blue water gently above all of that older history. Let the breath slow in time with the long, calm rhythm of a planet that has held many such cycles and that holds, even now, this moment in its ordinary patient way. The Mediterranean has been a sea and a desert and a sea again. Tonight, it is a sea. That is enough. There's no need to listen any further. Only rest now. The world, as it has always done, will keep its own time.